In this video, we're going to introduce the idea of a Taylor series or power series that is sort of related to those Taylor polynomials, right? And just as a reminder, let's write this down. So our nth degree Taylor polynomial, if we use our sigma form, which we introduced earlier, it looks like this, k going from 0 to n, right? That's the degree. And then these are the terms that we're summing up. So it's the kth derivative evaluated at a divided by k factorial times x minus a to the k, right? So again, this is our nth degree polynomial. Let's see, approximating whatever our original function is, f of x at x equals a, right? Now, I just want to remind you something. Back now we're coming back to the word series, right? But it seems like it's going to be a little bit more involved now. Remember that in fact, let me do it over here. So right here. So we have an infinite series that, let's say, k goes from 0 to infinity, and you have your terms here. And one way to really analyze these series is to say, okay, instead of thinking about this infinite summation, let's define the nth partial sum. In fact, let me go ahead and just, for simplicity, let's go ahead and make that 1, right? And then, so in this case, we only sum up the first n terms, right? And then we define the full series as the limit of this. So S, if this limit exists, right, it tells us, in fact, this limit tells us if our series converges, and depending on, if we have a nice formula for S sub n, we can know exactly what it converges to. And if you take a look at this, we have something very similar. We're starting at a certain value of k, we're going up to n, and the big question now is, what happens, right? So what happens to p sub n of x as n goes to infinity, right? But then the thing is, if n goes to infinity, we can't refer to it as a polynomial anymore, because a polynomial must have a finite degree, right? It must have a highest power of x. We love to say that about our polynomials. Well, now, if we let that highest power of x go to infinity, then suddenly there is no highest power of x, right? So what we want to do is just introduce some terminology, and there are some key concepts that we need to introduce as well that are related to these things that we're going to refer to as power series, right? So what is a power series? So a power series is an infinite series, but it has a little bit more. So it's an infinite series of the following form. All right. And so what is this form? Well, it is, I'm going to write it, k goes from 0 to infinity. And then you're going to have some coefficients that I'm just going to use c for coefficients. And what we have is something pretty familiar, especially with these Taylor polynomials. You have this quantity x minus a raised to the kth power. So it's of this particular form. And let me write out the expanded form now. So when k is equal to 0, you just have c sub 0. The x minus a to the 0th power will be equal to 1. And then the next term in this expansion, this power series, is when k is equal to 1, so you'd have c sub 1 and then times x minus a to the first power. I'm not going to write the 1 there. And then it just continues. C2 times x minus a squared, and then C3 times x minus a cubed, and then let's just say, and so on, right? And that's a power series. So the C's are just the coefficients. The A is referred to as the center. So let's write this down. So C sub k, this is the kth coefficient, right? Or let's just say, yeah, these are just our coefficients. And the number A is called the center of the power series. So the center of the power series. All right. Yeah, so what might they look like? So here's an example of one. And again, I'll start this one at k equals 0. And then I'll just do something like maybe -1 to the k. And then I'll have like x plus 5 to the kth power. Yeah, so that would be a power series. If we write it out, now that we have the actual formula for the coefficients and we know what a is, this is what it would look like. When k is equal to 0, everything here is equal to 1, right? So you'd start it at 1. When k is equal to 1, and this becomes a -1, so you'd have negative the quantity x plus 5 to the first power. I won't write that coefficient there. And then when k is equal to 2, you'll have a plus 1 times x plus 5 squared. And then when k is equal to 3, you'll have -1 times x plus 5 cubed, and so on. So it's an alternating series, right? In fact, if you look at this, you might say, well, it almost looks geometric, doesn't it? Right? Because you have this would be your first term, and it seems like you keep multiplying by x plus 5 or negative x plus 5 to get the successive terms. So I'm just going to say this one looks to be geometric, right? But what sets this apart is that in our previous look at geometric series or series in general, they didn't have the variables. And now we're essentially saying that now our series would have or has these variables, right? So it looks to be geometric. Here are the coefficients. Let me write it down, the coefficients. That would just be your -1 to the k. And here the center is at, now to identify it, since we're defining a power series to look like this, we would have to think of x plus 5 as x minus -5, so it fits our definition. So that means a is -5. So our center is at, I'll just say a equals -5, right? And that's what a power series is, right? Goes on forever. We have these now powers of either x or, in this case, x minus a, right? If a is equal to 0, right, then so if a is equal to 0, then our series just comes down to this. K goes from 0 to infinity. And then you'd have c sub k, and you'd have just times x to the k, and then it would look like this: c sub 0 plus c sub 1 x to the k plus c sub, just x to the first power, and then c sub 2 times x squared plus c sub 3 times x cubed, and so on, right? Now, let's just say a little bit about the coefficients. So remember, when we were doing our Taylor polynomials, we came up with a formula for these coefficients. Well, it turns out if we use those same coefficients, then we can refer to the power series as a Taylor series, right? And for us, they're going to be one and the same, right? So now let me remind you what the coefficients are for the Taylor polynomials. It's where you would take the kth derivative, and I'm gonna write it in the general case, and then you evaluate it at a, and then you divide by k factorial, right? So if we use that specific formula, right, that we came up with for those coefficients, then we can refer to our power series as a Taylor series, right? So the power series is also called a Taylor series, right? And then if A is equal to 0, then the Taylor series is called a Maclaurin series. So if A is equal to 0, the Taylor series is known as a Maclaurin series. So I know there are a lot of terms or names being thrown about, but basically in the context of what we're working on, power series, Taylor series, Maclaurin series, they're all in some ways referring to the same thing. Maybe slight differences, but power, Taylor, and Maclaurin, you kind of hear them in the same breath, right? So the question is, given a general power series, or maybe something more specific, a Taylor series, for what values of x will this series converge? That's the big. So that's the one of the big questions. So one big question is, for what values of x will a power series converge, right? So that's one thing. Another big question is this. Suppose I give you a function like, let's say, e to the x. Is there any way to expand that e to the x and make it into a power series, right? So given f of x, right, does f of x have what's called a power or Taylor or Maclaurin series expansion, right? So I'll just say power series expansion. For instance, you have something like x plus 4, that quantity cubed, and back in basic algebra you're asked to expand that polynomial, and then you would sort of FOIL it out. Well, that's kind of what we're asking here, but not for polynomials anymore. We're asking, can other functions be expanded, right, in this power series form? And we'll learn that a lot of the functions that you've studied in your basic and, let's say, pre-calculus courses, then a lot of those functions, they all have what we call a power series expansion, and we're going to learn how to find them. Right? But before we get to those, let's address the first question. For what values of x will a power series converge? Now, there's a theorem that explains basically there are three possibilities for a power series. And we saw two of those possibilities in the visualization that I previously did with Maple. Remember, in two of the functions, we were able to find essentially Taylor polynomials that would cover the entire function, no matter what the center is, right? No matter where the point of tangency was, and no matter how wide we made the window, we could always find a sequence of Taylor polynomials that would cover everything. But then we saw one where the function had a vertical asymptote, and we could only cover just a certain portion of that, right? Well, that fact is summarized in the form of this theorem, right? And it's not a theorem that we will prove. It's again, the proof of this is sort of beyond the scope of this particular course, but let's write it down. So for a power series, and here we're just going to use our generic form k going from 0 to infinity, and c sub k, and then I'll just have my x minus a to the kth power. So for a power series that looks like this, exactly one of the following is true. So exactly one of the following is true. And there are only three of them. Okay, so the first one that must be true, and this is the least interesting one, the series converges only for x equals a. So in other words, the only time I can get the series to converge to an actual number is by plugging in x equals a. And you can see what will happen if I plug x equals a in here, then I'll end up with 0. So basically, it's just a matter of zeroing out all the terms, right? So the series converges only for x equals a. For the second option, this is what we got a glimpse. We couldn't see it fully for obvious reasons, but remember when we were looking at the Taylor polynomials covering the sine and cosine functions, right? Well, when that happens, the power series converges for all real values of x. In fact, let me say this, it converges absolutely. So it converges absolutely for all real values of x. So it converges for all values of x. We're able to get it to cover a specific function no matter what x is. And then C, kind of the in-between now, the series converges absolutely for all x in some finite open interval. And what does that interval look like? Well, the interval it's centered at A. So, and then you go up a certain amount and you go down a certain amount. So it's going to be A minus R and then A plus R. So that's the interval here, right? Well, let me write it using our inequality. So it'd be A minus R is less than X, which is in turn less than A plus R. And diverges outside of this interval. So, and diverges if x is less than a minus r or x is greater than a plus r. right? Now, what happens at the endpoints? So at either endpoint of this interval, so at either endpoint, either x equals a minus r or x equals a plus r, the series may converge absolutely or conditionally, right? So may converge absolutely, may converge conditionally. Why did I put two T's there? So conditionally or diverge. So or diverge. So in other words, we don't know exactly what's going to happen at the endpoints. It could be any of our things that we've seen before in terms of absolute convergence, conditional convergence, or divergence. But this is, I guess you could say, the holy, or maybe not holy, but the trinity of power series, right? So visually, what does this really mean? Well, so the first case is basically saying that if you were to visualize this, so here would be so part A. Let me draw a line here. Right, so part A is basically saying this. You have your real line going from negative infinity to positive infinity, and you have your center here. And unfortunately, it's only at the center that the series converges. Right? It diverges for every other value of x. So pretty uninteresting. So diverges here, diverges there, right? For part B, it's this is the best you could hope for. So you have your real line again going from negative infinity to positive infinity. You do have your center, but now the series converges for all values of x there, right? So it converges for all values of x. Part C is referring to kind of an in-between. So again, here's our number line. This is for part C. We're going from negative infinity to positive infinity. There's our center. And now we have this sort of mysterious interval. And so here is A. So here is A minus R, and here is A plus R. And what the theorem says is as long as you stay inside this interval, right, you'll have absolute convergence, which is the best we can hope for. So we'll have converges there. But once you go strictly outside, so here or here, the series diverges, or power series will diverge. And then what happens at the endpoints, we don't know. So I'll just say at this value of x or this value of x, it's unknown, and it's something that you have to do case by case. It's not that you can't figure it out, but we don't have a single theorem that would always tell us what's going to happen at the endpoints, right? And the blue, right? The blue is what we refer to as the interval of convergence, right? So we're blue here. So let's just say this. So the interval of convergence, right? Let me say it this way. I think the easiest way, right, to use a word that I know you are familiar with. The interval of convergence is basically the domain of a power series. It's the values of x, right, that will produce a series that converges to a nice number, right? So now that it's like you now have a variable, and that variable will affect the result of the series. Does it add up to a nice number, or does it go to plus or minus infinity? So the easiest way I could say is that the interval of convergence is synonymous or equivalent to the domain of the power series, right? And then one more thing, just another term. So this R that shows up in part C, the third case, this distance R is, in fact, yeah, let me just draw it right here. So that distance R, which is the same as that distance, so that R is called the radius of convergence, because it starts from the center and you're only allowed to go out a certain amount. Once you stay within that certain distance, then you're guaranteed to have convergence, right? So R is known as the radius of convergence, right? So what can we say? So, I mean, I know R is only explicitly stated in part C, but technically, if the power series converges for all values of x, that would mean your R is infinite. In other words, the radius extends indefinitely in either direction. So it also applies to part B, and it also applies to part A. If the power series only converges at the center and for no other values of x, then that radius is 0. So over here, your radius of convergence is 0. Whereas in this case, your R is some finite number. So I'll basically say this. Here you go, right? And it's nice that in a power series there are only 3 possibilities, right? And we'll be able to determine which of these 3, right? So in this case, in this video, I again, it's getting close to 30 minutes in length. I wanted to kind of introduce this idea of a series that now involves a variable and how that variable affects the convergence. In our subsequent videos, we're going to work through a couple examples actually determining, whether the radius of convergence is infinity or if it's finite, right? So no specific examples in this video. I want you to think about these concepts, and then in the next video, we'll do some working examples that I'm sure will shed a lot more light on this. But the one thing I will leave you with is what we will use in actual problem solving are all the techniques that we did with our regular series, so to speak. So the series that didn't have variables, we will still be able to look for geometric patterns. We will still be able to possibly use ratio, root test, any of those tests that apply. And our goal here is to figure out where these series converge. Absolutely. All right, so I'll see you in the next video, and I promise it will make a lot of sense then. See you then.